Hello and welcome everyone to today's Infineon webinar on commercial vehicle applications. I'm Brian, your moderator, and we're excited to have 4 experts from Infineon with us. We've got Baptiste, Marketing Campaign Leader for Commercial Vehicles, Sijia, Global Application Manager for High Voltage Traction Inverters, Mahmoud, Global Application Director of Automotive Energy Management, and Daniel, he's the Global Application Manager for Onboard Charger and High Voltage DCDC. Now, our experts will present a video that covers electrified commercial vehicles, including traction inverters, battery management systems, and power conversion. So we'll start that shortly. Just remember, while the video plays, and I see the bunch of people coming in on the comment section already, while the video plays, drop your questions in the comment section and we'll try to answer them live there. And then, of course, we'll see you afterwards after the video. So let's get started with the presentation and enjoy.
Welcome everyone, and thank you for joining today's webinar. Today we're going to present you how Infineon is empowering the future of commercial vehicles with advanced semiconductor system solutions. And we're from Infineon, and let me introduce you the speakers. So my name is Baptiste Perier, and I'm leading the marketing campaign for commercial vehicles since December 2023 at Infineon. And together with me on the stage today, Sijia Zhang, our Global Application Manager for High Voltage Traction Inverter for both commercial vehicles and passenger car. Dr. Mahmoud Ismail, our Global Application Director of Automotive Energy Management. And last but not least, our Global Application Manager for Onboard Charger and High Voltage DCDC, Daniel Makus. In today's webinar, we will first start with an introduction about eCAV, and we will understand the difference with the passenger car. Then we will deep dive into 3 different applications to understand Infineon products and system for commercial vehicles. So starting with the traction inverter, followed by the battery management systems, and the last section will be dedicated for power conversion. So this webinar will last about 50 minutes and will be followed with a Q&A session. So let's get started with the introduction and let's understand what eCAV stands for. So eCAV stands for Electrified Commercial Construction and Agricultural Vehicles. And as you can see, there are mainly 3 types of vehicles. However, the focus for Infineon is on-road commercial vehicles because it represents roughly 80% of the market. And this is also where we see the innovation coming from first. Therefore, within these on-road commercial vehicles, we distinguish 2 types of vehicles, the e-truck and the e-bus. So the e-bus, they're mostly driven on city center and with many start and stop cycles and designed with longer operating time as well. On the other hand, we have the e-truck, usually classified by weight and use case. And here, below 16 tons, we refer to medium-duty trucks and above to heavy-duty trucks. And one example of heavy-duty trucks is the long-haul e-truck that is mostly driven on highway at high speed and where the goal is to minimize the loading capacity and to minimize the downtime. The electrification for this type of vehicle is supported mainly by the private sector. And the last use case that is worth to mention is the garbage e-truck in the sense that it's merging the requirements from e-bus but also long-haul e-truck. As it's driven in city center, so with many start and stop cycles, and also because it requires higher power to do its loading. The takeaway from this slide is to say that in the on-road commercial vehicles, this market is broad and there are many use cases to be covered, so from low to higher power range. Let's now understand the difference between a passenger car and an e-truck, and to say that it's not only about power. So we already spoke about the weight, that the e-truck is heavier than a car, but they're also designed for longer lifetime, so up to 1.5 million kilometers and up to 20 years, which means for semiconductor components, they also need to last longer. There are big diversity of mission profile. Here for heavy-duty truck, we refer to highly loaded and driven on highway at high speed. It's also different from the battery voltage. And the reason why it's because in a commercial vehicle, it can contain up to 8 battery packs, whereas a car usually contains only 1. Therefore, the battery voltage increase and can reach up to 1500 volts, such as the battery capacity. It's also different from the power rating because it requires higher power, so up to 500 kilowatts. So to say that in this on-road commercial vehicle market, we also see some new trends and new requirements coming from the OEMs. So starting with the automotive qualification that is required by European and American OEMs. We also see that there will be a need for higher safety standard in the future and for new fast charging standard, such as megawatt charging system, in order to reduce the downtime of the commercial vehicle. For all of these reasons, there is a need, and there will be a need for dedicated semiconductor products for commercial vehicles. And this is the good thing, because today we're going to explore Infineon solutions through the scope of 3 applications, which are crucial for commercial vehicles. So the first one will be the inverter system that will transform and convert the DC current from the battery to AC current to supply the motor. And here with Sijia, we're going to learn more about the one inverter, one Infineon. Then it will be followed with the battery management system with the primary function to monitor and manage the health, safety and performance of the battery. And last but not least, we will look at the power conversion solutions of Infineon for commercial vehicles. So both internally, so inside the commercial vehicles, and also in connection with the grid and the charging infrastructure. So with this introduction, I have the pleasure to hand it over to Sijia that will present you Infineon traction inverter system solution.
Thank you very much, Baptiste, for giving a very nice introduction of commercial and agriculture vehicle. So now we're moving to the second chapter, which is focusing on a very essential application, the traction inverter. Traction inverter is very important for eCAV because it determines the driving behavior of either the truck or the e-bus. According to the legacy, usually the traction inverter is placed centrally on the chassis, as you see in the middle of this car. But we do see more and more of a trend that the traction inverter is directly integrated in the e-axle on the bottom part of the chassis. And by doing that, we actually get more efficiency and the cost space optimization. Knowing the trend, we will also love to bring you up towards how big is the total addressable market in the eCAV traction inverter. Starting this year until the end of 2029, we're looking at a very lucrative market. In 2029, we're talking about a total addressable market for semiconductor around about 800 million. And this is largely categorized into 3 different regions. Those are the Greater China area, those are the European area, and as well as in US. China is, of course, leading in the e-truck and e-bus arena, having a market share in that year around about 50%, followed up with US and Europe. That being said, we also see some of the leading trends in this application for the inverter. Those 4 areas are dependability, high load, modular and scalability, as well as of high switching frequencies. If we look at each of those, let me quickly drive you into the depths of each of these 4. Dependability, also known as reliability, because e-bus and e-truck, they have a very long operational time and much harsher environment to operate compared to a passenger vehicle. We're actually talking about close to 1.5 million kilometers in a lifetime, roughly 20 years. And that's calling for extremely low fit rate, eventually quality leadership. The second trend is in high load. Sometimes you need really high output current, eventually translating into close up to 500 or 400 kilowatt continuous power. The third trend is modular and scalability. You do see some of the players in this market, the tier 1s, they're trying to synergize between passenger vehicle as well as CEV, and that's calling for a scalable platform approach for fast time to market and reduced design effort. The last trend is in higher switching frequency. Higher switching frequency eventually would lead to less losses. and translate into a longer range for the e-bus and e-truck. Having said those 4 areas, I would also be very proud to show that at Infineon, we do have this so-called one inverter, one Infineon approach, which is valid both for passenger vehicle and commercial agriculture vehicle. Here we have a very nice success story with one of the leading OEM in China, Yutong e-bus. If you look at the statistic in 2022, this year, Yutong is number 2 in the whole globe, coming to the total sold e-bus and e-truck combined. And there you have the 32-bit AURIX microcontroller TC27, as well as the Econo Power, which is a half-bridge power module inside of this very nice, very green e-bus. So we do offer, actually, in addition to the power and logic, OD component. For those interested, here is the block diagram. I'm not going to dive into the details, but feel free to visit our webpage by clicking on this QR code and do a deeper dive into all the components, ranging from power module to sensors, as well as to logic and the power supply PMIC. So here, looking at the market competition landscape, Infineon actually is the only person who can offer all the components inside the traction inverter for CAV. So we do have microcontroller, the power supply for microcontroller, the PMIC, the current sensors, as well as power stage and the gate drivers. Looking into details, there are 2 boards I would love to recommend. There's the logic board where microcontroller is mounted. There is also the power board with the 2nd generation hybrid kit on top of this. And those are already available, which is even adding to the good news in the market. You can order using the SP code listed here and have your hands already a first base touch of our next generation power as well as our logic devices. In addition to that, we also offer industry grading reference design. Here you have one nice example with EconoDual, as well as our current sensor and gate driver, and also the whole total system addressable mostly for Asia customers who not necessarily have to step into automotive grading and will be very happy already with the industry offerings. This reference design we recently showcased in our PCIM about 3 weeks ago, and you will have the reference design ready in the market in last quarter of this year. So now I'm going to give you a deep dive into each of those components. The EconoDual is a proof of concept, has been widely adopted, as you see before, for instance, with the Chinese OEM already in the market. It's a half-bridge module which can go up to 900 amps. And you would also have the latest generation available. The hybrid pack drive is an automotive graded power module, which is a full 6-pack and a full bridge module. From the sinterable technology, this one we also sometimes funnily call it the power of the dark side, because it uses the black surfacing, which is actually a sinterable technology which boosts up the output current even higher versus its predecessor family. It's a star product, has been sold more than 5 million pieces in the market, and in the 2nd generation, we make it compatible also with the ICE gate driver 3rd generation, as well as the current sensor, which can be easily mounted into the tabs of the HP drive. Now coming to what we mentioned before, the scalability and modular approach. This is calling also on the power product portfolio to have the full scalability ranging from different voltage class as well as a fully compatible packaging option. So here you have a choice very widely spread across silicon carbide as well as IGBT. Here we already have the 2nd generation first samples available, and some of those has been already a proof of concept since last year October in some of the leading passenger vehicle OEM globally. Now on the gate driver side, the 3rd generation gate driver is optimized for silicon carbide and hence supporting very fast switching frequencies. So have a look at that too. And eventually on the microcontroller arena, the TC3XX, the 2nd generation of AURIX, has a very nice feature called the integrated resolver interface. As you know previously, to understand the rotor positioning, you would require an external IC, sometimes known as Tamagawa or ADC. But this kind of hassle is no longer the case in our TC3XX family. Here we have using delta sigma ADC, as you see on the bottom side of the RX microcontroller block diagram, to get rid of this resolver interface. Eventually, you're saving the total BOM of around about $10 and the additional effort of doing the wiring. So here you also have a nice system integration into into a functionality integrated inside the microcontroller. Having said that, thanks for taking your time checking out all the new information and products on the traction inverter world. With that, I would love to hand over to my colleague Mahmoud on the battery management systems.
Thank you, Sijia. I will be proceeding now with the battery management systems. So, first of all, what's driving the battery management systems in electric commercial vehicles? The key topic here is the lithiumification of electric vehicles. And the reason you're going to see a lot of lithium-ion batteries is that because lithium-ion batteries, compared to classical type of chemistries, have much more energy and power density. For example, in comparison to legacy type of products like lead acid and nickel cadmium. This makes them actually compact enough so that they can actually sit in a vehicle. Additionally, they usually have much longer lifetime, which makes them also more economically viable to be used over the life cycle of a vehicle. As well as lithium happens to be abundant, and with the right processes, it could be extracted in an environmental friendly way, and as such, you have an environmental friendly vehicle. But why would a lithium-ion battery require BMS? And the key reason in that is the complexity of the chemistry and the cell stacking. Usually you deal with cells that usually have sub 4 volts in voltage, meaning that if you want to build up a pack of 400 or 800 volts, you have to stack a lot of these cells. Stacking these cells means you will have some kind of misbalancement, for example, due to different thermal distribution across the battery. This misbalancement would lead to a charge type of misbalancement. And since lithium-ion type of chemistries are usually rather complex and have a very complex type of characteristics, small changes between the cells can lead to big changes in the overall performance of the battery. This means that if you miss any small changes, you could operate the battery outside their spec operations and outside its safe operating zone area, which actually can lead to things as catastrophic as thermal runaway. And here the key point is to understand is that the pack in a battery, no matter how big it is, it behaves as the weakest cell. So one single cell can actually influence the entire performance of the pack. That's why you will need a battery management system. A battery management system is basically, you can look at it as the nervous system of the body. It's actually the intelligence which is responsible for monitoring the battery cells, keeping the battery safe, and maximizing the performance of the battery. So let's look now at an electric commercial vehicle battery and how they look like and what are the key challenges there and how we can actually address them with Infineon solution battery management systems. Here's a little example on cell chemistry. If you look at different type of chemistries, you can see that they have one thing in common, which is their voltage slopes are rather flat, meaning that, for example, based on the voltage sensing, you can see that you can have high error estimations. In any error in the voltage sensing, you can see that you have a high error estimation of the state of charge. This even gets more extreme if you're dealing with state of health, because lithium-ion chemistries usually can survive up to 80% of the state of health. After that, they tend to degrade very fast. This means that 1% error in your state of health could be translated to 5% error in the remaining usable life. And this can become quite catastrophic, especially in commercial vehicles, where your battery could be of an average size of 400 kilowatt hours, which means at a $120 per kilowatt hour, this battery is around $48,000 just in cells. 1% error in your state of charge prediction, it means you have either oversized the battery by $480 or you need to oversize your battery by $480. Other way to look at it is that this error in 1% error in the state of charge is losing you 4 kilometers in range. And on the state of health, because it's even bigger and has to do with the capex of your battery, you're actually losing for every 1% error in your state of health $2,400. And errors of 1% is actually quite low. You would not be surprised to see in batteries errors of up to 5%, which makes these numbers much bigger. And additional to that, what you usually have in the commercial vehicles is that these batteries are quite large, not only because of their voltages, but also they need to pack more range in them. And you can see, depending on the platform, you can have a lot of parallelization of these packs, which means that variations between the packs could very much impact also the performance of your vehicle. So let's see what the key tasks of the BMS is to achieve in electric vehicles. The first one, it needs to maximize the battery range. So every kilometer matters. It also needs to maximize the battery lifetime, because in commercial vehicles, the capex needs to be split over a longer period of time for the investment to make sense for the vehicle owner and the fleet manager. It also needs to minimize the downtime, because especially in commercial vehicles, every second counts. And finally, it has to be safe, because you're operating a vehicle on much more frequent than a classical passenger vehicles. Their failures could occur earlier, and you need to be able to predict them and mitigate them. So how we are doing this? The first way is we're trying to improve the performance of the battery by using advanced sensing features. For example, if you look at the cell stack on the left side, what we do is that we have BMS ICs that have a very advanced type of ADC architecture that can guarantee the accuracy over the entire lifetime at very sub 2 millivolt levels. We also have integrated into our BMS ICs a so-called stress sensors, which compensate to any mechanical aging or mechanical stress effects. So this is so that the ADCs are maintained their accuracies. We also introduce, for example, digital filters, which actually makes you independent of external filters, which actually age even faster than your electronics, your silicon electronics, and can actually also participate in the lowering the accuracy of your total measurement of your ADC. We also have introduced a one ADC architecture, which means that we are able to measure all cells at the same time, which is particularly important if you want to do something like electroimpedance spectroscopy. And here also we have advanced pack sensing solutions that allow you to do also advanced type of measurements, like, for example, electroimpedance spectroscopy. We also are improving our solutions by introducing new computational features, like, for example, our new TC4 family with an integrated PPU, which is a hardware accelerator for advanced type of battery cells. You can run there your model-based solutions like MATLAB Simulink, as well as deploy your AI type of solutions, which comes, for example, from the TensorFlow. This will actually enable you to run really advanced type of battery models like state of charge, state of power, state of health, predict lithium plating in advance, without the fear that you actually are completely occupying your microcontroller capacity to a point that it actually becomes neither economic nor safe. And lastly, we're adding advanced protection type of solutions. We have new thermal runaway type of prediction solutions, whether it is using temperature, voltage, pressure, or gas sensing, that are both GTR20 phase 1 and phase 2 compliant. We also have advanced disconnect solutions, from classical contactor drivers to solid-state contactor that are compliant to ISO DAS 5474-3, which can give you actually a faster disconnection in special cases, especially during megawatt charging for megawatt charging solutions. And lastly, we have also advanced battery passports that are automotive grade, that give you a secure passport so that you actually make sure that no one has tampered with the battery history or tried to actually hack the battery or modify the battery. I will now show in short glance all the products that today are used in the high voltage BMS, that we're actually with that enabling all the features that I just mentioned. So let's start with the cell sensing and monitoring. Cell sensing and monitoring is very important because, as I said, you will be stacking a lot of cells. And if you look at an 800 volt system, you can stack anywhere between 180 and 220 supercells. These supercells, they will start having some kind of misbalancement, and this balancement is important to address because, as you notice on the right side image, if you actually don't address this misbalancement during charging and discharging cycles, you will always have a certain capacity that you're not able to charge or discharge, and as such you're driving around with a very heavy battery that you're not allowed to fully utilize. For that, we have our TLE9012 with very high accurate lithium-ion battery monitoring and balancing IC. It's an ASIL-D rated, and it actually fulfills all the features that I mentioned earlier. Next, you want to measure the current and you want to monitor the pack. And this is very important because during driving, the voltage is not enough for you to actually predict the battery states. You will need to also predict something like the current, because once you put a load on and the temperatures start to variate in your pack, your battery states start drifting. For example, the state of charge. For that, you could do something called a Coulomb count, since all these cells will share the same current. There are two ways to measure the current. One way is to use a hole-based sensing. Our TLE4973, for example, are used as a solutions for predicting very fast overcurrent events. Or you can go much more accurate with a shunt type of solutions with our PSOC HVPA. The PSOC HVPA has a high precision analog on it, which enables it to actually measure the current really accurate, as well as it offers a daisy chain configurability so that you can synchronize the voltage and the current measurement. There are multiple ways you can use these products. One way, for example, the advantage of the hole sensing is that you can click them either on the high side or the low side of the bar, and you don't need to worry about isolation because they are isolated. The PSOC HVPA on the other side family is actually connected always on the low side with the shunt. We offer two options with a single shunt and dual shunt depending on the ASIL rating that you want to achieve. And lastly, we have a hybrid type of solutions where you can actually leverage the additional ports that you have inside the PSOC HVPA to connect a hole sensing to it. And as such, you can have a hybrid type and a certain technological type of redundancy for both accurate as well as fast response to current changes. Now, once you collected the voltages and the currents, you actually want to communicate them, usually to a mic controller. However, your mic controller would be sitting on the 12 volt domain, which basically it is grounded to the chassis, whereas your battery has to be isolated all the time. So this means that to communicate between your mic controller and your analog front ends, you need some kind of an effective type of isolation. For that, we have three different types of solutions. We offer our TLE9015, which is an ISO-UART transceiver. For daisy type of chain of topologies, we have our CYW8982X, which are automotive grade Bluetooth 5.0 and 5.4 SoCs. And we have also ISOphase, which is an automotive grade digital isolator. You could use these solutions in different type of topologies. In a classical type of topology, for example, you can connect your TLE9012 devices in a daisy chain, and you can have your pack monitoring device separately on an ISOphase connected to the CAN. In a more advanced type of solutions where you need to synchronize current and voltage, you can actually add your PSOC HVPA directly into the daisy chain and use your ISO-UR transceiver to actually manage the isolation of the circuit. And lastly, you can also use your HVPA as a gateway with an ISO phase on the CAN. And lastly is you can actually simply isolate every single one of these devices or a group of these devices using our automotive grade Bluetooth. This is particularly beneficial when you are going really high voltages, for example, 1400 volts and above. Now, once you collected all these voltages and currents, you actually want to process them and make something out of them. Usually on your mic controller, you have a software. This software runs 3 layers. Your lowest levels, where you have all the drivers. Then you have your middleware, where you have your complex device drivers. And then you have the application level, which takes care of all the battery states, as well as all the logging events and all the communication events. One of the key challenges in the BMS is not only to take care of all the safety, but also to have enough computational power to compute these states. These states could be as simple as lookup tables, electrochemical models, get more complex like Kalman filters, machine learning models, or hybrid models where you have multiple of these models, or as highly complex as digital twins. Anything that is less than a digital twin could be computed directly on the vehicle level, and anything above a digital twin and above could be computed on the cloud. And for that, we offer 3 kinds of solutions. You can go with a Traveo if you don't have too much computation to run and you have a simpler models and you're fine with ASIL-B, or an RX-TC3 family if you need an ASIL-D solution and an additional computational power. And if you're going really advanced algorithms, like for example simplified digital twins or machine learning type of solutions, or Kalman filter or matrix, where you have matrix operations, there will be RX-TC4 family with a PPU. And of course, using our PMIC, you will allow for an ASIL-D type of solution. Now that you actually computed everything in the battery, you want to try to protect this battery. The first thing you look at when you're protecting the battery is you look if the isolation has broken. Here we use the PSOC HVPA as well, which can offer actually isolation monitoring as well as disconnection monitoring. We also have additional three families of measurements that would allow us to predict events like thermal runaway. You can use the temperature and the voltage, for example. You can also use the gas state, whether it's the concentration or the pressure inside the pack, or you could use the electroimpedance spectroscopy to actually predict. And you can see the more you go downwards, the earlier you can predict a thermal runaway event. So you can, for example, measure your voltage and temperature simply using the TLE9012 devices, the ambient sensing using our extensive pressure and gas sensors, and you can connect them to the different places in your battery. On the electroimpedance spectroscopy, you can simply daisy chain your pack monitoring, which is the PSOC HVPA, together with the TLE912, and you will allow a synchronous voltage current measurement. Here's an example of an additional product which I just mentioned, which is the pressure sensor. The KP467 is a very advanced type of pressure sensor designed especially for this type of application, where it actually also enables GTR20 not only phase 1 but also phase 2 for standby for parking mode thermal runaway detection. Lastly, once a thermal event has happened or any critical event has happened, you want to disconnect the battery. The battery disconnection usually is used for not only disconnection, but also for connecting the battery. So for example, when you turn on your vehicle, you want to connect the battery. When you stop your vehicle, you want to disconnect the battery. Or for example, if any critical event like a crash or an overcurrent event happens, you also want to disconnect the battery. For that, you could use, for example, our low voltage switches or our smart switches for driving mechanical disconnects. The way you usually do it is that you put these switches around your mechanical disconnects on both the high side and the low side to enable a certain type of redundancy, as well as to have a capability to modulate on one of the sides so that you actually can turn on your mechanical relay smoothly enough without aging it or damaging it. Alternatively, you could also use the high voltage switches. For example, our CoolSiC 1200 and 750 volts in combination with our ICE drivers, high voltage ICE drivers. These type of solutions will enable something we call solid state contactors, and these solid state contactors would actually allow you to disconnect the battery much faster, like sub 10 microseconds, compared to a mechanical contactor which takes milliseconds. So when an overcurrent event happens, you don't actually have to worry about very high currents that will damage the circuitry and make your vehicle not drivable anymore. And with that, I conclude my part and I pass next to my colleague Daniel Makus.
Hello everyone, and thank you Mahmoud for giving me the stage. My name is Daniel Makus. I'm Application Director for Power Management in Automotive. And today we talk about power conversion in commercial vehicle, especially in electrical commercial vehicles. Let's have a look a little bit more closer. What is the power conversion in electrical commercial vehicle? We have a DC to DC converters, we have DC to DC and DC to AC converter for high voltage. And we have also the charging equipment, which is super important for commercial vehicles because it's different to normal personal vehicles. And I would like to start immediately with the charging of electrical vehicles in commercial segments because it's quite complex. Let's have a look a little bit more deeper. In a charging, we can differentiate AC charging, you see on the top side, where complete electronics will be in a vehicle. One of the difference of this charging is due to electronics in the vehicle, the charging power is usually much lower. And thus, it's usually used in a smaller commercial electrical vehicles. Where the lower part of the slide, you see the DC charging system, which is outsourced to the DC charging stations, where space, performance and other parameters are totally different. And the power levels can reach multiple megawatt hours, and also charge time for the electrical vehicle will be much shorter. Let's have a look a little bit more deeper. What are the differences? On this slide you see different charging powers for commercial vehicles you see. And we differentiate basically between the different stages of charging. For example, in home or harbor charging, we can charge up to 100 kilowatt because the time for charging is not critical. Moving in the middle, where destination charging, we need much more power because charging time is typically super critical. We are less than 2 hours parking time where charge need to be completed. And finally, if you look to more right side of the slide, we see super fast charging required where, for example, on a highways or on very short stops, the electrical commercial vehicle need to be charged. And with this, the high or super high power charging is required. Compared to personal vehicles, we talk about charging powers of less than 22 kilowatt. And with this, of course, we can charge also commercial vehicles if the time is not critical. But let's have a look a little bit more deeper how charging stations can be built. On the left side, you see one so-called monolithic or all-in-one systems where all charging power modules are in one systems. The advantage of this system is it takes very little space for installation, but disadvantage, of course, the scalability, but also the charging power is limited. The solution for much higher power charging stations will be on the right side, where you see highly modular, highly flexible systems where power is in so-called dispenser or in a cabinet. These solutions can scale to up to 3 megawatts and enable multiple chargers to charge the electrical commercial vehicles much faster or also charging the fleets. If you look a little bit more closer what kind of parameters and also trends are visible in the charging domain for electrical commercial vehicles. Of course, we talk about the charging power you see on the left side. It's super important because depends on the size and use of the commercial vehicle, charging power will demand the time for charge. Well, with the increase of charging power, the power density becomes super important because space for all these cabinets become super important, especially if the installation is in a city or in an urban area where space is critical. And with this, of course, the charging power manufacturer look for scalability. to expand the charging power in future if it's not enough, or maybe further charging stations are needed. If we combine all these features with technologies and solutions we need, we clearly see the need of moving of technologies from silicon of yesterday and today to silicon carbide in future charging systems, because charging power, charging density, but also modularity is much easier to implement. If you look a little bit more closer to the topologies we see, we will identify that not only the silicon carbide is the solution, but also the combination of silicon carbide and the higher voltage capabilities of this technology. Because the DC link voltage of the super high charging power stations will increase to 1500 volt, where traditional topologies will become rather complex or limited. That's why the 2 kV silicon carbide is an appropriate solution for the future technologies. And you see here on this slide multiple implementations of solutions. From the left side, 2-level designs up to the cascade and multi-level designs on the right side. Shows the complication of the solution, but the good message is Infineon has all required components to make the charging solution reliable, powerful, but also super power dense with new power technologies. If you look a little bit more on the AC charging side and the power DC to DC, the world is a little bit different. The AC charging is slower, as we learned. Electronics is in the car. So the high power density is a super key feature in this application. So we need to define the solution and provide a solution to the customer, fulfilling all these requirements. In the middle, you see the power conversion, and you see the complexity of this application. We see many different rails, 24 volts, standby solutions, 24 volts, up to 5 kilowatt for traditional loads, for the body units, for the fans, for any kind of compressors. And we see also HV to HV power conversion, for example, for fuel cell trucks, where the power levels can go to multiple hundreds of kilowatts. And again, it's also here, high performance, high power density at high efficiency will play a super important role, because everything is integrated in the vehicle. But if you look a little bit more deeper, what kind of topologies and solution we see in the onboard charger, also for commercial vehicles. You see on the left side, 2 specific topologies which define different worldwide standards. For example, in the middle, totem pole PFC will be implemented on a single or dual phase application, for example, for Chinese, American, maybe Japanese market, yeah? Where the B6 or B8 solution you see on the far left side is typically representing the 3-phase solution in Europe or any other country which has a 3-phase installation on the AC side. For the DC to DC as a part of the onboard charger, we see on the right side different topologies. Again, here also depends on application requirements from the truck, from the battery of the truck, from the power levels, different topologies can be selected. Typical one we'll see in future, dual active bridge and also CLC. Why CLC and dual active bridge? Because it's also capable of bidirectionality. Because for commercial trucks, bidirectionality may play a role, especially for the fleet services, for the buses, where energy can store in the truck, but also to be used for energy use cases, reducing the total operation cost of a truck and also giving another business services. Looking to the solution of those topologies, again, we need the proper technology. And here we see, depends on the selection of topology, we have low voltage silicon carbide, silicon IGBT technologies, but we have also for the 3-phase and also high voltage battery solutions with 1200 volt, 1500 volt and 2 kV solutions in the future. Let's have a look a little bit more in the DC to DC. Very similar to the high voltage part of the onboard charger, we see here different topologies. On the high voltage side, you see on the left side of the slide, we see typical topologies represented by phase shift full bridge or phase shift full bridge with sync rectification. This is very common topologies in a high voltage DC to DC converter, which implement this very easily and also with available solution, very easy to control in total. Here, typical topologies can be implemented with technologies coming from the silicon, IGBT, and also silicon carbide. Of course, the tendency here is also silicon carbide because it's enabled higher power density, higher efficiency, and higher performance, of course, in total. Looking more to the left side, to the right side of the slide, we see the secondary side. So which is the low voltage side, 12 or 24 volt solutions, in some cases even 48 volt solutions, where we need the transistors with less breakdown voltage, typically less than 200. What we see here, phase shifted full bridge topologies or active clamp forward topologies, which can be implemented rather with 100 volt, 120 volt, or in some cases even lower voltage solutions. So in total, you see, we have, from transistor point of view, very nice solution scope. We have different solutions fitting to topologies, different solution enabling the optimization on the topology level and also on the complete application. But it's not all. We see many more components required in this application. Again, power converter, it's all about power. You see on the left side, all three columns, high voltage stage, PFC for the DC to DC or the charging station, the DC to DC in the middle, and also low voltage side. It's all dominates the topologies for power. Technologies selected for these topologies are listed here. So we support CoolMOS, CoolSiC, IGBT in any kind of packages, because scalability in this application plays a super important role. Similar, you see on the medium side for the voltage, low voltage. Smaller packages, packages with high power density are super important and a key for designers to select. But what to do with the transistors if there's nothing to control? So here it's super important to have a gate driver, proper gate driver, fitting the technologies, fitting to the power levels, fitting to the isolation levels. Here Infineon offers the complete span of the gate drivers, supporting not only the technologies, but also individual topologies, enabling the isolation levels, enabling the right support on the digital side, right optimization for the power converters. Going a bit more further, you see many more components required in these applications. We talk about the current sensors. Many current sensors are needed in AC to DC application in order to make the control easier, reliable, but also safe, especially with the new features like the bidirectionality. We need to implement the safety features, and here Infineon offers current sensor solutions which enable the application to behave safety, enable the security levels in the super small space on a PCB. And finally, software control and power supply for the microcontroller. Microcontroller will be more and more important functionality in the power conversion because new topologies demand for much higher power levels, for more complex control loops, and with this, our topologies are supported with AURIX, but also with industrial microcontrollers coming from XMC families. And of course, connected to the microcontrollers, the PMIC solutions, which enable not only safe operation, but also reliable supply. And finally, the software. Why software is needed? Again, topologies become very complex in power conversion, and we need to provide the customer the software support algorithms for design time improvements, for reliability, for testing, and also for very early stage on simulation. So all in one, we provide as Infineon the complete solution for power conversion in commercial electrical vehicles. But that's not all. What we also provide is many reference design kits which enable immediate evaluation of new power topologies, new application, new combination of the power systems. Let's have a look a little bit closer to that. On this page, we see DC EV charging topologies and the reference kits which support the customer evaluation immediately. 11 kilowatt, 22 high power up to 50 kilowatt units available from Infineon to evaluate, to start the design immediately. Looking closer to the onboard charger DCDC, we see ultra tiny boxes enables the AC to DC conversion immediately. Customer can take the solution, evaluate, and start very fast. And looking to more future gallium nitride will become a new technology of the state-of-the-art solutions, enable higher power density, high flexibility, but also lower cost. Also here, we prepared already first solutions which customer can evaluate and get the first impression of technologies and solution for the future application, minimizing the power conversion, making this more efficient, but also more flexible. That's it from my side. All in one, Power conversion in electrical truck and CAV is super important. So it's enable all crucial functionalities. No power, no functionalities. Very, very clear. And also, we support the charging, which is also very crucial for operation. And for every solution, every component is available for Infineon, for performance, for optimization, for scalability. With this, I would like to give over to Baptiste for Q&A session. Many thanks.
Thank you very much, Daniel, for presenting our power conversion solutions. And with this closes the webinar session. And before wrapping it up, I would like you to show this slide with the supporting material. So feel free to scan the QR code that is available on this slide. This will lead you to our promo page, where you will find further information about the product and the solutions that we presented here today. And now we will be back in a few minutes to open the Q&A session. Thank you.
But thanks for the great video. It was very informative, and we had a lot of good questions and answers here. And traction inverters, battery management systems, and thanks to Sijia for introducing us to the power of the dark side for a change. In terms of hybrid power modules, Sijia, you mentioned that the hybrid solution for 1200 and 1700 volts is not available for the open market, and you're starting with 750 volts. Is that your plan going forward, or are you looking to expand that lineup?
Yeah, so correct. So you can refer to the chat history. So basically, we do have right now already planned 750 voltage module, so the 6-pack in hybrid pack drive package. This will be upcoming in the middle of next year. We're also looking at the feasibility of what is mentioned here, so 1200 volts. And here, if you have leading customers, of course, we're willing to see if there's any possibility to bring this into the roadmap item. But to further confirm this, yes, we're looking at this right now. There is a good possibility that we will have it with an SOP date in the end of 2026. Yeah.
Okay, great. And then Mahmoud, you mentioned that the battery management system, you supporting sustainability through secure battery passports and higher accuracy sensing solutions. Is that something that you're finding is taking off in the industry?
Yes. So basically, first of all, the battery passport recyclability and second life is definitely now taking off. The life cycle of the battery is still a little bit, I would say, people are still trying to understand it. I think some of the OEMs starting to grasp that, but I think many are still kind of like too much busy with what happens with my car at the beginning of life. For these OEMs to think 10, 20, 30 years down the road, what happens to the battery, I think it's not still yet at its full steam. But I think with time we're going to start seeing, especially once the warranties for batteries start being questioned, and if the passenger actually is, when they're returning their battery, is actually the state that is said on their battery, there will be third parties that will be double checking if this is true or not, and that's where I think many OEMs will start jumping on the wagon and start saying, okay, I want to have more advanced BMSs, which actually shows more details into my battery.
Okay, and then for our chat, we do have a few minutes left. If you have any further questions, I'd just like to check with Daniel. From your perspective, what are some of the most exciting trends in power conversion technology that you're seeing right now? And how are you positioning yourself to lead in that area?
Yeah, well, it's a very good question. Actually, since demand for high power is really the key in this all applications, so we have a lot of resulting trends out of that. So, for example, give you one perspective. So, if in the past we talked about a 2 kilowatt DC to DC converter in the space of 1 liter, now it's actually double power or even more power in the same dimension. So even if a truck supposed to be much bigger, in space, the integration of the components are very dense because they're all closer to the inverter or charging inlet. So we see this as one of the major driver for a lot of innovation in that system. So That's why many technologies plays their role, not only on the front end, but also on the back end. So package itself plays a big role, but also innovation on topologies.
Very interesting. Giuseppe asks if the presentation will be available. Yes, you will be able to get it on Elektor TV Industry on YouTube. And Baptiste, I see, has already answered that. Baptiste, you're on top of that. And what do you find, how is the reception being regarding the marketing for commercial vehicles, electrified commercial vehicles at Infineon?
Yeah, I would say that the interest is growing over the years. We have seen more applications and more interest from customer side and from the OEMs, because we explained there is a need for dedicated products. So there is also a need of adaptation from the OEM side. And yeah, those three applications that we presented today are crucial. And yeah, this is also one of the reasons why we wanted to focus today on these ones. So growing interest and yeah, many more to come in the future.
Awesome. You did have a QR code in your presentation. Some people might not be able to scan it or don't want to scan a QR code. I took the liberty of getting the URL. If anyone can see that on screen, you're welcome to type that in. I won't keep it there too long, so you can pause here if you need to find more information from Infineon. Any more questions in the Q&A? Emil has some interesting points. He says that, this is quite a long one, high voltage was mentioned a few times for future commercial vehicle applications. What about technology direction evaluation and capability in both known econo-dual hybrid package, for example, moving away from bond wires or modification material substrate, reducing thermal resistance and changing filling materials, etc.? Anyone want to give a short answer to a long question?
Yeah, it will be a long answer, unfortunately. So first of all, the differentiation between an econo-dual and hybrid pack drive, it's more focusing on automotive grading. So econo-dual today, it's focusing on non-automotive grading. This is especially needed, for instance, in China. And hybrid pack drive, this is for automotive grading, which is largely adopted in Europe and in US, especially, for instance, big OEMs in Europe like Volvo Truck and Daimler Truck. In the future, so depending on exactly what timeline you're talking about. So at the moment, we're more looking for off-shelf products. This is largely accepted by major tier ones and OEMs because they want to have faster time to the market. Therefore, a ready-made power module, either half bridge or full bridge, depending on whether automotive grading is needed, will be of choice. For the long run, if you're looking at the manufacturing with the SOP larger than 2027, 2028, we do see some of the people are talking about optimization and tailor-made products. In this context, there are people already looking at, for instance, being more aggressive on, for instance, discrete solutions and sometimes even on a bare die solution. But as for today, for the next 3 years, the off-shelf product, especially in ready-made power modules, like mentioned, these two products here will still be in the mainstream. Yeah.
Okay, and I think we have time for one more question. What about cooling? What temperature ranges for cooling fluid will they be with future materials like silicon carbide and gallium carbide?
It's very difficult to answer right now because actually Infineon itself is not working on the cooling concept, but we do have a few partners in the industrial. So for instance, there's a German-based company called Quada, which we're working together in terms of the cooling. And we have a few of distribution partners like in China with the G-Pulse from Intron, for instance, that they also have their own cooling concept. So to quickly answer which temperature, sorry, I cannot do it, but feel free if you want to contact our partner on that one. I think there's also a second part of the question on GaN, or somehow it's got blocked with the chat.
There it is on
Okay.
screen.
Yes, there's also one question in terms of silicon GaN. To put it very short, for the eCAV right now and for the next 3 to 4 years, that is until like 2028, we hardly see GaN. it will be more on thick and on an optimized SiC or IGBT. So for instance, fusion concept of full SiC equipment or IGBT. So at the moment, the GaN is more planned, I would say, in the time frame of 2029 onwards for the inverter application. It's a different story when it comes to onboard charger. So if maybe Daniel, you want to comment a little bit on the onboard charger, because it's the penetration rate for GaN is much earlier in onboard charger compared to inverter. Yeah.
Yeah, absolutely. Maybe if we take the power conversion in one, of course, the strive for high power density absolutely leads to evaluation of new wide bandgap materials. This is very clear. On the other side, if we look to the mission profiles of the truck driving millions of kilometers, so the early stage new technology usually is not the preferred choice. That's why in the truck domain, eCAV, buses, doesn't matter, we see the dominant position of silicon carbide in the next year or maybe even decade. If we look a little bit in the body business, body control business, where potentially the new domain zone architecture become more and more in volume, the air-cooled system potentially play an important role, especially in power conversion. And this is exactly the sweet spot which we can immediately address with gallium nitride, because power density, high power efficiency will be the solution for air-cooled designs. And there's also a link to the question before, maybe a comment from my side. Today we usually liquid cooled, so the temperatures are well in, I would say, in the reasonable areas. But for the cost saving in future systems, a lot of OEMs and tier ones are looking for air-cooled systems. And this could be exactly linked to this new packaging solutions like Sijia mentioned with Quadar and so on. So a lot of innovation is expected there. It's very clear also for the onboard charger.
Well, thanks for that. We've run up against our time. You know, the depth of knowledge here could take an 8-hour presentation, but with the brains in this room, I think for 1 hour, the audience got their values worth for sure. And you could probably watch it again, catch it on Elektor Industry TV. Just thank everyone for joining us from around the world with all your questions and comments. And a big thank you to the brains in the house, Baptiste and Sijia and Mahmoud and Daniel. Thank you all for joining us today. And to our audience, if you have any more questions, you've got the link, so feel free to reach out through Infineon's website. Thanks once again for joining us, and have a great rest of the day, everyone.